3 times, this wheel will turn once. You guys see that? Because say you're constantly looking at this one point here. Every time this motor turns around, you'll see 10 teeth go by, right? Which means it's pulled 10 teeth worth of chain along. But here, pulling 10 teeth of this sprocket along is only a third of it, okay? So we say that our gear ratio is a 3 to 1, right? So every time this one turns 3 times, this one turns once, okay? So say we got this motor and it's turning at 1,000. Oh, that's a bad number. 1,000 RPM. How fast is this wheel going to turn?
3 point.
Right.
No, 3.
350
point. Yeah.
RPM.
Keep going.
Or so. Right? So the speed is reduced, but the torque is increased by that same amount. Okay? So say we got 1 foot-pound of torque coming out of this motor at 1,000 RPM. Right? We now have what? 3 foot-pounds at this axle. 3 foot-pounds. Okay? So that's it. And so that we know that if our wheel is 6 inches, right? This radius is what? 3 inches. What did I say it was? 1 foot-pound. And this is 3 foot-pound. So if this is only 3 inches, how much force can we push against the floor? Is it? Right, so it's more. Right, so.
3 pounds.
So we have 3 foot-pounds, right? But our lever arm here is only 3 inches, right? So that's equal to 3 inches is a quarter of a foot, right? Feet times how much force? What times 0.25 would make these two things equal? 12. 12 times 4. Okay, so we would actually be able to push this way, saying we're rotating this way, right? Push against the floor with 12 pounds of force. Is that correct? Do you guys see how that works? Right, okay, so right. So 3 pounds. Right, because if we have 12 pounds, and instead of, right, so 3 inches times 12 pounds, right? And there's 12 inches in a foot. Inches cancel out. You have 36 over 12 equals 3 foot-pounds. Okay?
History day.
Huh?
History day.
project.
History.
Slept at 4:30 yesterday.
Good story, bro.
What?
Oh, they had a history day project, so they pretty much did a whole bunch of stuff till late at night.
Okay.
How we're recording this
So
conversation.
And that's why you,
So please don't be offended.
Yeah, so I'm not trying to, it's just,
but do you guys understand what's going on or
yeah.
not?
No, keep recording.
It's still recording.
Honesty is the best policy.
Okay, Wayne.
Yeah,
Wasn't even full,
that's true.
Honesty is the best policy.
Okay, so Kimmy, what is our actual gear?
My brain. It is 15 and, okay, 15 on the drive axle, or the motor, gearbox axle sprocket, and then 22 on the wheel sprocket.
And we have a 6-inch wheel?
Yeah.
Okay. So. 6 inches, and you have what?
What do you got? Let's see.
22?
22, 2,
And on the tough box, you have what?
15, 2.
15. And then what's the gear ratio of the tough box itself?
I believe it's 12 to 1.
I don't think so. 12 to 1?
No, it's 6 to 1. No, 12, I think.
it is.
Or, I think it's 12 to 1.
The
That one,
oth-
the
the
top
other-
boxes are
Yeah,
12 to
they're 12.
1.
The other ones are
Yeah,
5
the
or 6.
Sims are.
Okay,
6 to
well,
1.
let's just assume
And
it's
then the
12.
ridiculous ones are like 81 to 1.
What is that?
12 to 1. And then, so 15 to 22 is what?
15 to
What's 22 divided by 15? It's 1 point something.
Just think of 20%.
It's between 1 and 2.
27.
It's about 0.7.
Oh, sorry, 20.
22 divided by 15?
Okay. Oh, the other way around.
1.4 to 1?
1.46. 6.
Okay, so say we get 12 to 1 out of the tough box, 1.46 to 1 out of this 15 to 22. So what's our total gear reduction is actually these two numbers multiply
17.52.
17 point what?
52.
5, close enough. Okay, so what's the maximum RPM of the sim motor? Where's Sam go? Sam.
Sam.
Maximum RPM of a sim motor.
Maximum 5,500.
At 12 volts?
Oh, 12 volts? I don't know.
Really?
I thought it was
5,000. That's pretty nice.
That's not the
It literally was.
Super sound. Super sound.
So while Sam is looking, can I introduce myself?
Okay,
Over
sure.
here. Just gonna reduce my stranger danger. My name is Justin Koo. I'm gonna be helping out with the Robotic Club. I work across the hallway with Dr. Siu. I'm his partner. So my background
the
is
camera.
my background is mechanical engineering, and I work with electrical engineers, mostly operations, manufacturing, project management. So hopefully I can help you guys out. So right now I'm really focused on helping with Samuel and Sam in the schedule. So trying to get you guys back on track. I think you guys right now are a week and a half behind. So I don't want you guys to be doing test and debugging during the competition. So that's not good. So we'll see what I can do to help you guys pull the schedule.
Okay, thanks. And if I'm telling him anything wrong,
You're doing fine.
let's see. So, Sam, maximum RPM.
It is, so 5,310 with no load.
So I'll just call it 5,000. Okay. So if our sim motor is going 5,000 RPM, how fast is our wheel turning? Calculator, get a calculator, jeez.
5,000 divided by 17. 285.7.
280, close enough. So our wheel is going 285 RPM. So, what's our theoretical top speed?
ID. So each rotation is about 18 inches of travel.
Okay.
Just use 18 inches.
18 as 18.84. 56.52 inches. Oh, that's. Wait. Is that 6-inch radius or 6-inch diameter? Yeah, 6-inch
Diameter.
6-inch diameter. 6.14 times 6. Who told me 18.84? 18.84.
What?
18.84. So that means. Wait, oh, sorry.
Inches.
Yeah, inches.
Wrong. So it's 18.84 inches per rev.
Yeah.
These cancel out.
18.
How many minutes in an hour?
Times 285. 5,369.4 resolutions per inches per minute.
What is that? Well, no, let's, inches per minute. So, 12 inches in a foot, right? How many feet in a mile?
5,280.
What?
5,280.
Right, 5280 feet in a mile. And how many minutes in an hour? 60 an hour. So minutes are gone, inches are gone, feet are gone. This equals what?
Miles per hour.
6 divided by 12. Divided by 2080. Divided by. No. Times 60. 5.08.
Really?
Pretty slow.
That's really. Sure?
And that's, right, with the sim motor going at its absolute maximum speed, all our drag being 0. The top speed is 5 miles per hour.
Wait, is this for the launcher or the actual driver?
This is for the drive
This
train.
is divided by
He's
12. I did divide by 12.
So is that fast enough?
see where.
It's not walking speed, is it? Yeah. Or light jog.
But because of the inefficiencies of the motor and all
You
the
expect a lot
friction of your roller chains, your sprockets, your bearings, the rug, I don't expect you'll get anywhere near.
Sure, 5,000 is the maximum RPM.
Yeah, that actually sounds pretty high for that big of a motor. So if Sam's lying to us, it could be even less. See that thing? So, you guys have it working, right? You can actually, have you guys actually driven the thing around?
Yes.
Jerry has
Wait, we have.
driven donuts around the
Jerry?
hotel, which was fun.
Jerry did donuts like it was
Yep.
Oakland and in front of the Coliseum.
I saw the video. Was that recent?
Yes, that was very recent.
I think that's
I hope Jerry wasn't there.
That was Jerry.
It was taking our robot.
So the normal load is 4,300. Free load is 5,300.
Okay.
So under load is 4,300.
4,300.
So it's about 20% less than what we get. So we'll probably get about 4 miles.
Faster than some people can walk.
right? But how long is that gonna take us to go from the feeder station to, right, at
Precious
least
time.
40 feet away?
Precious time.
It's about 4.4 or 5.
Right, so it's 4 or 5 miles an hour faster than Burris?
The field is 50 meters long, isn't it?
54.
54 feet,
Feet.
yes.
It's a
Remember,
really long field.
you're in America.
Meters.
Feet.
Yeah. Seriously. Right.
Meters.
You want meters, you gotta go to Canada.
We are the liters of this club.
Oh.
I think that's what you feel
that
like.
was
Recorded for all time.
Yeah, it's being recorded.
forever on record, Sam. Forever on record.
It's okay, this first thing he's done in his life.
Okay,
Oh, yeah. What?
Just to provide an anecdotal story, this is a problem Tesla had. You guys know who Tesla is, right? When they built the first Roadster, it was actually designed with 2 gears. But the gears kept breaking and it delayed to release production for the Roadster. So they actually had to settle for 1 gear in the car. So they sacrificed top speed to compromise the 1 gear. So I'm sure that they had sleepless nights doing this kind of calculations.
Thankfully, the Roadster's not even known for its top speed. It's just the ridiculous acceleration.
No, it looks nice.
alright.
Sub 4, sub 3 second, 0 to 65.
Yeah, it's wonderful.
No, now the Nissan Leaf and the Prius can do that.
Gosh.
Prius very aggressive.
Okay, so when you guys give the robot back together, why is it taken apart again?
It's taken apart?
I mean, all the electrical's off that board again.
I don't think that the electrical stuff was ever on that board.
It was
No,
mounted.
it's
It was
because
on
they had the
it.
wood thing on top,
Actually-
didn't they? They had the wood thing on top and then they
Well,
tested
anyway,
it.
next time you guys get it back together and do actual real driving test, see if you can actually figure out a way to measure how fast the thing is going. Okay? Yeah, you can do it Mythbuster style if you want.
We already did that with the Frisbee. With
Okay.
limited success.
And see if it's fast enough. And if not,
Use the vernier.
you guys know what to do to make it faster?
If you physics.
We could change. Oh yeah, you guys have that sensor, right?
Yeah.
Lab Pro, which is actually big enough to do that.
Yes.
Not photo
Yeah, we don't
gates,
break
the
them.
vernier Lab
Well,
Pro.
no, either one would work.
Oh, fine, really?
Either
Oh, yeah,
one
yeah.
would work
Well,
because
with-
one is you just measure that time it took
That's
and you
true.
set a certain distance
have
apart.
a
The other
small-
one you actually use
It's
the
very
sensor.
small.
We could have a little antenna up on.
Yes, I'll bring my chrono and we'll shove the robot through it.
Okay,
Oh, yeah.
alright. You guys all understand this, right? Any questions? Again, I'm gonna erase all this now.
Is this
Okay.
what you do in engineering school?
I didn't go to insurance. No, I'm just-
Flying by speed.
Oh, I'm never gonna be an engineer then.
No, in engineering school, you use computers.
Okay, good.
So at least you know what to tell
Let's see
the
if we can
computer to
talk
do.
about unpaid interns.
Okay, so,
Terrible person.
next subject, pneumatics. You guys are gonna use pneumatics, right? So what are pneumatics?
Hydraulics without the hydro.
It's hydraulics with pneuma.
Hydraulics use liquids.
It's
Yeah, so hydraulics without the hydro.
It's you use your
With the
lungs,
new.
your breath
The
to.
new.
The new.
You breathe and it powers the robot.
Those compressors.
Pneumatics are
Air.
air pistons that use air as the fluid.
Yeah.
Operating, what is it? Pascal's wager.
Right?
Pascal,
The end result-
Pascal's law, right?
Yeah.
Is that you're gonna have this pneumatic piston. Right?
Would you
So
like
this
us
is
to bring one in?
Say you took this cylinder and just cut it. Do you have an example? Have you guys all seen the pneumatic cylinder?
They already have it, like,
Huh?
they already built some systems with it,
right? Do you know how it works?
Like a paper.
somewhat.
Okay. Well, we'll go over that one in detail. So yeah, you do. And the next time I ask you that, you say yes. Okay, so.
Pneumatic is, yeah.
There's a hood.
So, what, it uses compressed air to push it up and then creates.
Pneumatic piston. Hey, so say we took this piston and I just cut it right down. Alright?
I charge you money. Overpriced.
Don't challenge me. Okay? So the way this works is there's two holes, right? So this is just an empty tube with a rod in it, right? There's an air seal here. And at the end of the rod is a disc that's the same size as the inside bore of this piston. Okay? There's two inlet outlet or air ports on it. Okay? So because this cylinder, this disc is practically the same diameter as the inside bore of this, very little air. You know, this creates a seal here, and there's very little air that goes from one chamber. So if you were to pump air, molecules into this port of the cylinder, it pushes the rod out. Okay? So you put air in here, it pushes on this disc that's in there, and it pushes the rod out until it reaches assuming that this just exhausts into the air, it'll go until, as long as you pump enough air in here to push this up, it will go until it stops. Then if you want it to retract it, you push it, you leave this one open to the air, and then you start pumping air into here, and then the piston retracts, okay? So, you can use these to exert a large amount of force in a straight line. Now, mechanically, when you use them, you only want this to apply the force in a straight line. Usually, the ends are mounted on a swivel, so that you can't apply some sort of bending force on this, right? Because I've seen where people have taken this end, right, and if you solidly mounted this to something, and then solidly mounted this to something else, right, applying a force on this part here can cause this to try to bend, okay? And that would be very bad, because if you bend this rod, it would, all right, affect the seal here, cause it to leak and not function anymore. And these aren't designed to take forces like that, okay, bending forces. They're only meant to exert straight forces, in line with the rod itself, okay? And that's why they'll be swivel mounted. So say you use this to open the trunk of a car, right? It would push up, and the trunk of the car itself would be fully constrained to just rotating up and down by the hinges of that. And this has to be on a swiveled end so that it can follow that path as the trunk opens and closes, okay? And not cause damage to the piston. Okay, so all right, so to control the airflow, we use solenoid valves. Okay, so say you have an air hose coming to here. This air hose will have a source of high pressured air and have actually two electrical connections. there are two main types of solenoid valves. There's a spring return type, where if you energize, you apply the voltage, proper voltage to the solenoid. There's actually a little coil in there, electromagnet, that will cause the valve to change positions, okay? Then if you remove the voltage applied to it, there's a little spring that will return it back to its normal position, okay? So, so internally, right, this, say this line is a hose, its normal position may be that there's actually an inlet and an outlet on the solenoid. Its normal position may be to connect this output hose to the exhaust, so this is just open to the air. So if you were to push on this, the air inside this chamber would go down the hose through this valve and then out to the atmosphere, okay? Then when you energize it, say you have high pressure air here, you energize it, flicks it to the other side, then this high pressure of air, because the pressure in here is higher than the pressure in here, right? Because you've exhausted this, it's now at atmospheric pressure. The air will flow, right? So say we energize it and now it's connected that way. The air will flow through here and then push the piston out, okay? There's another kind of solenoid valve that actually has two coils in it. It's, I think they call it a double acting solenoid valve. It's the type that's on last year's robot. Energizing one coil causes the valve to flip one way and stay there until the other coil is energized, then it pushes the valve the other way, okay? So they call them double acting or latching because you energize it and you de-energize it, but it stays in that position that you sent it to, okay? Let's see, so I don't remember, are there, on last year's robot, were there two solenoids per cylinder or just one?